Hey, thanks for tuning in. Welcome to Nomadic Geek. In this tutorial, we'll be using the ESP32-CAM to control a relay through a web dashboard. Learn how to create a dynamic dashboard that activates a relay with ease. This tutorial is perfect for enhancing your skills and expanding your knowledge of IoT. So, grab your ESP32-CAM or favorite Arduino and let's get started. Let us first take a look at what we need for this tutorial. A relay is an electrically operated switch that opens and closes the circuit to control the flow of electricity. It's essentially a switch that is operated by an electromagnet, which is triggered by a voltage or current. The relay acts as a middleman between the control circuit and the load circuit, and it can be used to control high voltage or high power circuits with low power signals. They're often used in automated systems to control lighting, heating, cooling, and other electrical systems. The ESP32-CAM is a module based on the ESP32 microcontroller, which is a powerful, low-cost, and low-power platform that is well suited for IoT applications. The module is equipped with a camera and can be used for a variety of applications, including video streaming and image capture. It has built-in Bluetooth and Wi-Fi, making it well-suited for our project. An FTDI converter is a device that converts serial signals into USB signals. The FTDI converter is used to interface between a computer and a device that uses a serial interface, such as the ESP32-CAM module. Please hit the like button, subscribe to our channel, and turn on notifications for more tutorials like this. And don't hesitate to leave a comment with any questions or thoughts you may have. Now that we're all set, let's dive in and start controlling that relay. Are you ready? Let's get started. If you haven't already, you need to install the ESP32 board in the Arduino IDE. If you need instructions how to do that, you can either click the card on the screen or find a link to the short instructional video in the description after watching this video. In the top of our code, we have some includes. An include directive is a preprocessor directive that tells the compiler to include the contents of another file into the source code. This allows for code reuse and helps to make the code easier to maintain and modify. This header file contains my personal Wi-Fi SSID and password to avoid the risk of revealing it to the internet. This file contains definitions, structures, and functions for controlling the camera and capturing images or videos. This provides access to the Wi-Fi functionalities of the ESP32 microcontroller. This provides access to the Websockets functionality. This line sets the camera model to the AI Thinker model. This is necessary to configure the camera pins correctly, as different camera models use different pin configurations. This provides access to the standard input-output library of C, which includes functions for input-output operations, like reading from and writing to the serial interface. This header file contains definitions for the camera pins, such as the pin numbers for power, data, and control signals. The ESP32-CAM module has a built-in flashlight on pin number 4 of the ESP32, which we will use in conjunction with the relay for demonstration purposes. So, we define the flash _ pin as pin 4, and the relay _1 pin as 12. These two lines of code define two constant character pointers, SSID and password, and initialize them with the values of network _name and password respectively. You will need to replace them with the actual values for your own network, as you can see in the comments. SSID is the name of the Wi-Fi network you see when connecting to it from, as an example, a smartphone, and the password is its password. This line defines the IP address of the computer that will host the Node.js server we will write later in this tutorial. And the line below is the port, which you can leave as it is. An IP address is a unique numerical label assigned to a device connected to a network that identifies the device and its location, allowing it to communicate with other devices on the network. If you need instructions how to check your computer's IP address, you can either click the card on the screen or find a link to the short instructional video in the description after watching this video. We create an integer for both the flashlight and the relay so that we can keep track of their state, on or off, as a 0 and 1. Using namespace WebSockets is a C++ directive to include all the symbols and entities defined within the WebSockets namespace into the global one. WebSockets client just declares an instance of the WebSockets client class. Further, we have a function that we use for handling WebSocket events. It takes two parameters, event and data, which are the event and its accompanying data, respectively. The function checks the type of the event and outputs a corresponding message to the serial monitor. If the event is a connection closed event, the ESP module is restarted. This ensures that the module continuously tries to establish a connection to the server, which I will explain why further down in the code. The function onMessageCallback is for handling incoming messages from a WebSocket connection. The function takes a single parameter, a WebSockets message object, which represents a message received from the WebSocket connection. The function then extracts a key and a value from the data contained in the message by using the index of and substring methods of the string class. Depending on the key, the function updates the state of either the onboard LED or the relay by setting the corresponding digital output pin high or low. The function also prints the key and value to the serial monitor for debugging purposes. This is the setup function, which is one of the two mandatory functions in an Arduino sketch. This function is executed once when the Arduino board is powered on or reset. The purpose of the setup function is to initialize any necessary resources, such as setting the pin modes, initializing libraries, or connecting to a network. The reason why we have the restart of the ESP32-CAM in the function above is to run this setup function over and over until the connection is established. The first rows in the setup function sets up the configuration of the camera module by initializing a camera_config_t struct named config. It sets the LED channel, LED timer, and pins for various signals including clock signals, vertical sync signal, horizontal reference signal, and power signals, among others. It also sets the clock frequency, pixel format, frame size, JPEG quality, and number of frame buffers. Then, we initializes the camera with the specified configuration, checks if the initialization is successful, and retrieves the camera sensor object. It then sets the contrast, raw gamma, and vertical flip of the sensor to flip the image captured by the sensor vertically so that it appears upside down. After that, it starts a connection with the specified Wi-Fi network and waits until the connection is established. Then, it sets the mode of the two pins for the LED and relay as outputs. You can later revisit the code and remove the line set_v flip if the images from your device are upside down. These two lines are calling the two functions onMessageCallback and onEventsCallback that were added earlier in the code to handle WebSocket connection events and message events, respectively. These functions are being registered with the client object so that they can be triggered when the corresponding events occur during the WebSocket communication. Then we initializes the serial communication with a baud rate of 115,200 bits per second so that we can send and receive data to the serial monitor. Then we connect to the Node.js server. The while loop continues to execute until the connection is established. If the connection fails, the loop will wait for 500 milliseconds before trying to connect again. So, to summarize the lifecycle of the program so far, when the ESP32-CAM is powered on, it will run the setup function and then set up the callback functions defined at the top of the code. It will remain in the while loop until a connection to the Node.js server is established. If the connection is lost at any point, the onEventsCallback event handler will run, causing the ESP32-CAM to restart itself. Every time it is powered on, it will run the setup function and try to connect to the Node.js server repeatedly until a connection is successfully established. And when that happens, the second mandatory function of an Arduino sketch runs, the loop function. This function is executed repeatedly, allowing the ESP32-CAM to perform its tasks continuously, such as receiving and processing messages, reading data from sensors, and controlling actuators, while it remains connected to the Node.js server. The first line of the loop function, client.poll, checks for incoming messages or events from the WebSocket connection. If a new frame buffer, an image, is available from the camera, ESP-camera FB-get is used to retrieve it. If the frame buffer is not available, the function returns immediately. The next step is to send the binary data of the frame buffer to the Node.js server using client.sendBinary. The frame buffer is then returned to the camera using ESP-camera FB-return. After sending the frame buffer, a string with the state of the flash LED and relay is constructed and printed to the serial monitor for debugging purposes. The state can be either on or off. Finally, the state string is sent to the Node.js server using client.send. That's all for the ESP32-CAM. Upload your code to the board so we can move on to writing the code for our Node.js server. If you need instructions on how to upload your code to your ESP32-CAM module, you can either click the card on the screen or find a link to the short instructional video in the description after watching this video. For writing our Node.js server, you may use the Integrated Development Environment (IDE) of your preference, but in this video, I am demonstrating the use of Visual Studio Code, VS Code. Here we have our project. We have a file explorer located on the left side, where all of our project files are stored. It consists of a public folder which holds all the files that are accessible from the client side. Then we have our package.json, which contains important information about the project, such as scripts and version numbers, amongst others, and is necessary for using NPM, the package manager for Node.js. And lastly, the server.js, which is the core of our project, where all the server-side logic and functionality are defined and implemented. As you can see, I have the package.json file open. When you initialize a Node.js project with npm in it, the package.json file is automatically created and provides you with the opportunity to specify important details such as the name, author, description, and more for your project. You can always modify these details later on within this file. If you need instructions on how to create a project from scratch this way, you can either click the card on the screen or find a link to the short instructional video in the description after watching this video. These are the dependencies that the project is using. Express is a fast, minimalist web framework for Node.js. It provides a lot of the functionality needed for a web application, including routing and middleware, and makes it easier to build a server. The path module provides utilities for working with file and directory paths in Node.js. It allows you to manipulate file paths in a way that is platform independent, so you can write code that works the same on Windows, Mac OS, and Linux. The WS module provides a WebSocket implementation. WebSockets allow real-time communication between a server and client and are commonly used for things like chat applications and online games. The WS module provides a simple way to work with WebSockets in Node.js. To install a dependency, you can use the Node Package Manager command line tool. The npm tool is installed with Node.js and can be used to install packages from the npm registry. If you need instructions on how to install Node.js and its package manager, you can either click the card on the screen or find a link to the short instructional video in the description after watching this video. The script section of our package.json file in Node.js defines command line scripts that can be run using npm. In this specific case, we have two scripts defined. Test. This script is supposed to run tests for your application, but as the script itself says, it just returns an error message indicating that no test is specified. Start. This script is more important and is used to start the server. It specifies that when the command npm start is run, The script should run the server.js file using the node command. These scripts can be run from the command line by running npm run script name. For example, to start the server, you would run npm run start. The require statement in JavaScript is used to include external modules in a Node.js application. It allows you to reuse code across your application and is equivalent to importing libraries or modules in other programming languages. And we save them as constants. We create an instance of the Express application. We set up a static file server using the Express static middleware. It maps the URL/static to our public folder in the project directory, the folder that is exposed to the clients to read the HTML, JavaScript, and graphics within it. We create an array named clients which will later be used to store connected WebSocket clients. We create a constant named http_port which holds the value of 8000. This is the port that the HTTP server will listen on and is used to connect to by the clients. These lines of code creates an object named devices that contains information about a device named relay_module 1. The information about the device is stored as an object within the devices object with a port property set to the value 8888. This information is used later in the code to define the port on which the server will listen for incoming connections from the device. This code is setting up a listener for an uncaught exception event. When such an event occurs, it logs the error and the origin of the error to the console, along with a message indicating the status. This code sets up a WebSocket server on port 8999 and listens for incoming connections. When a connection is established, the connection event is fired and a new WebSocket instance is created to represent the connection. The code listens for messages sent by the client and then tries to parse the data as a JSON object. If the data represents a command operation, the code looks up the recipient device in the device's object and sets the command property to the message key and value. The code within the try-catch block processes the incoming data in the WebSocket connection. If the data is not in a valid JSON format or if there is any error, the code in the catch block ignores the error and continues to listen for new messages. This code creates WebSocket servers for each device defined in the device's object. The WebSocket server listens for incoming connections on the specified port, which is stored in the port property of each device object. For each connection, the WebSocket instance representing the connection listens for incoming messages. If a command is available in the device object, it sends the command to the connected device. If the incoming message is an object, it sets the image property of the device object to a base 64 encoded string representation of the data. If the incoming message is a string, it splits it by commas and creates a key value object to store peripheral data. The device's object is then sent to all clients connected to the WebSocket server. Finally, we create a route with the URL path/client. When this route is requested by a client, the server sends back the file located at the path/public/client.html. The path.resolve method is used to get the absolute path of the file to be sent, and the send file method is used to send the file back to the client. And we start the HTTP server and listens on port HTTP_port, which was previously defined as 8000. The public folder contains the client-side components of the web page, including the client.css file for styling, the client.html file for the page structure, and the client.js file for the page's functionality. These files work together to create the final presentation of the web page on the client's device. This is a basic HTML structure for a web page called client. The content of the web page is placed inside a division element with an ID of main wrapper. This main wrapper element is used to render all the JavaScript-generated elements on the page. The page includes two resources which are linked through the script and link tags. The script tag is linking to client.js, while the link tag is linking to client.css. The static folder is the virtual path that is mapped to the actual public folder. This allows the server to serve the static files to the client when requested, as the static folder is the endpoint that is made publicly accessible by the Express static middleware. In the client.js, we have the logic for the presentation. This code creates a new WebSocket connection to the server at its IP and port. Once the WebSocket is open, a message is sent to the server with an operation of connecting, along with an empty data object. This message is sent in JSON string format. The following code is a WebSocket event listener that listens for incoming messages from the server. The WS object is a WebSocket instance that has already been established with a connection. The listener function is triggered every time a message is received from the server. The message data is expected to be in JSON format and is parsed into a JavaScript object called MD. The function then loops through each device in MD devices. If a device is not present in the HTML document, it creates the necessary elements to display information about the device. The elements include a main div container with an ID matching the device's ID, a header h2 element, an image img element, and a div container for holding command buttons. If the device has an image, the source of the image img element is updated with the base 64 encoded image data received from the server. If the device has peripheral devices, the function loops through each peripheral device and creates command buttons if the buttons don't already exist. Each button has an ID matching the ID of the peripheral device, a state icon that displays whether the peripheral is on or off, and an event listener that listens for clicks on the button. The event listener sends a command to the server via the WebSocket connection, indicating the desired state change for the peripheral. If the peripheral device already exists, the function checks if its state has changed, and if so, updates the state icon accordingly. The client.css file is responsible for styling, including positioning and appearance. We are controlling the appearance and position of the HTML body, the item cards, the commands buttons, and the icon for on and off. Let's try it all out. We try to start the server. We have to install the Express module. We try again. Now the server starts. And as evidenced by the output in the serial monitor, communication has been established between the server and the ESP32-CAM. Let's try if we can see anything in the client. All seems to work as it should. We can both turn on the LED as well as the relay controlling the LED bar. Let's take a look at how the relay should be connected and then summarize the commands flow, from button pushed in the dashboard on the client to the relay connected to the ESP32-CAM. This is how we connect if we are using a 5-volt relay. This is because the ESP32-CAM module can output 5 volt on its 5V pin. This is how we connect it for a 12-volt relay, which is the one I am currently using. The ESP32-CAM is just connected to the ground and signal pin on GPIO 12, and the power is provided from the 12-volt battery. This is how it could look like in an installation. Let us go through the flow now. When When the button is clicked, an event handler is triggered, which sends a WebSockets message to the server with an operation of command and the data containing the state of the device and its reference. The server gets the message, and as the operation is set to command, it sets the command to the device object. When the server receives a message from the device with a pending command, it sends the command to the device in return and then sets the command to null, indicating that it has been processed and consumed. The ESP32-CAM module gets the message and triggers onMessage, which call the onMessage callback function. The messages contain either onboard LED 1 or Relay 1 as the key and 1 or 0 as the value. The relay receives a high signal to turn on the connected peripheral. The variable holding the state gets a 1 instead of 0. The new state is sent back to the server, causing the icon on the dashboard to turn yellow. This allows the client to send the next command of 0, which turns off the relay. And that concludes this tutorial. If you enjoyed what you saw, make sure to hit the subscribe button and give this video a big like. That way, you'll never miss a single one of my future uploads. And if you have any ideas for topics you'd like to see me cover in the future, drop a comment below. Your feedback and suggestions are always appreciated. So until next time, farewell and keep on learning.